Hello, I am audible, right? Hello.
Yes, sir.
Yes, sir, you are audible.
Okay. Okay. So good evening, everyone. So let's start today's session. So the first question of today is this is the question from GATE 2012 Metallurgical Engineering. The flotation beneficiation is based on the principle of option A mineral surface hydrophobicity, option B gravity difference, option C chemical reactivity, and option D particle size difference. So anyone want to approach this question? This is a one mark question, so
I
very
think
straightforward.
it should be mineral surface
Ye-
hydrophobicity.
Okay, mineral surface hydrophobicity. Okay, what is the beneficiation? Do you know? Miss, what is the definition of beneficiation?
It's like a process from a mixture, a process of separating a particular component.
Yes, yes. Okay. So so let us discuss the flotation process first. So in flotation process, the this is based on the principle or based on the difference of the surface hydrophobicity of the minerals and the gang material present. Means in the mineral, ore and gang materials both are present, right? So this technique is based on the principle that the difference in the hydrophobicity of the ore and the gang material which is present in the minerals. So is, is the images are visible properly on? Okay, I think it is visible now. Yeah.
It's visible, sir.
Mhm. So in this process, what we do, like you have the powder material in the form mineral in the powdered form, then you mix it with the water and a small amount of pine oil. Then through this tube, a compressed air is passed in through the system. So it does basically it agitates the whole system and generates a air bubble which creates a froth on the uh, layer of the oil. So what happens, the hydrophobicity of the ore particle is more, so it attaches with this air bubble and it goes up with the froth, and then it is collected in a separate container. Like in this video also you can see. So this is a pine oil and this is the water. So now you are putting the powder ore in this chamber, and then you are passing the compressed air through this blower. Then this air is creating froth in the oil layer. So the oil level is going upwards up to the surface level, and it is also attracting the ore particle with it, and then it is being collected in a separate container. Then it will be dried, and then cleaned. Then you will get the concentrated ore of this of that metals. So now this is the uh, froth flotation. So now you know this is based on the principle of surface hydrophobicity. And the next one is gravity difference. Anyone has any idea in gravity difference which process is follows this principle?
Sir,
Gravity difference.
tabling.
Yes, yes. So yes, hydraulic washing or gravity separator. This technique is based on the principle that the different density of your ore will have the different settling rate or terminal velocity. So what will happen? Let's say this is in this technique. you spread your powder material in a slope block, then uh, the the streamline of this water is coming, which which will wash away the finer particle or lighter particle, and the heavier particle will settle down. So in this way, we will get the distribution of the particle size, means particle density wise, you will get the distribution in the different groups. So lighter material will like washed away, and then it will separate in the different groups, right? So this technique is gravity difference. Anyone have any idea in nature, did you find anywhere this gravity separation techniques works, like?
So like whenever it rains, after
Hmm.
some time that inside that mud, the soil particles settle down and the water comes up.
Yes, yes, this is also one thing. And in terms of mineral beneficiation or mineral processing, if you see in the shore area, there you will find that the fine sand particle, that this is the lighter color or golden color sand particle will you will find near the sea, near the shore. And the black sand, which is mostly contain the ilmenite, which is the ore of FET, means mostly titanium is extracted from this ore. So you will find this black sand at the means at a distance from this your shore. So why this is happening? Why you are getting this kind of distribution, like here the black sand is here and then the golden.
Sir, because the density of titanium is greater than silica. Like or normal sand contains silica, but like
Yes.
titanium is heavier than silica.
Yes. So when the wave is coming, that time what is happening, because of the turbulence, all the materials are mixed together, right? Now, when the waves hit the shore, that time what happens? The most of the kinetic energy of that waves is absorbed by the sands. So now when the waves is going back, that time it has lesser kinetic energy. So what happens that time? The ilmenite or the black sand, which contains the FeTiO3, so it contains iron and titanium, which is much heavier than your silicon or normal sand. So this sand is settled down fast, and then the finer sand particle, which is washed away with your wave, and it settle down afterwards. So that's why in nature also you will get this kind of distribution. Here also the gravity separation techniques or gravity difference, this principle works. And in first option, in the surface hydrophobicity, did you know anything in what you do in the daily life in this? Have you do you have any example of this hydrophobicity, like where
Sir, that
this?
some
Hmm.
of like for example, the when it rains down, it will like wet the entire surface, but the leaves of the plants do not wet so much. So
Yeah, that is like how different wetting ability you are describing. But here, what is happening depending on the hydrophobicity, this technique. Uh,
For washing clothes.
Yes, exactly. So when you are washing your cloth using soap water, what happens that soap water, that hydrophobic side of your soap water, it is attached with the your dust particle, and then it actually clean your cloth like this, like it is attached with the dust particle, and that bubble actually come out of your at the top with along with your dust particle. If you soak your dirty cloth in soap water for a few times, you will see that the will get dirty, right? So why this is happening, this is also same principle is acting there also in the hydrophobicity uh, of your particle. So in froth flotation, mostly sulfide ores, beneficiation of sulfide ore is mostly people do the beneficiation of sulfide ores in froth flotation process. And What is the third option? That is a chemical reactivity. So which process is is based on this principle, chemical reactivity? Anyone? Chemical reactivity means, let's say you have
This one, the precipitation, sir.
precipitation in the sense this is in the mineral
So, like for
beneficiation.
example, if,
Hmm.
if suppose in a chemical solution we add certain reagents,
Hmm.
then at a fixed some of the elements they react together and they precipitate out, like they form a solid mass, and the
Hmm.
rest of the elements remain in the solution.
Yeah. So what this process is called? Do you remember? It is called selective leaching, right?
So cementation. Ah, yeah, selective. Yes,
Leaching.
sir.
Yes. So one example is your bauxite ore of aluminium, right? So there with Al2O3 we also have SiO2. So we have to separate the SiO2 from the Al2O3, right? So in this case, your that powder ore of bauxite is dissolved in a sodium hydroxide, liquid sodium hydroxide, aqueous solution of sodium hydroxide. So it formed that sodium uh, aluminate. Also that silica which is present in the bauxite, it is also dissolved in the sodium hydroxide, and it also forms sodium silicate. So now what happened, both dissolved with the your sodium hydroxide solution, but all the other particles or other gang material that will get precipitate. Now in the solution you have both the sodium aluminate, which where aluminum is there, and also silicate. But silicate this one is unwanted for you, right? So you only need the aluminum base ore. So that's why then we pass the CO2 to precipitate out this aqueous means hydrated Al2O3, and sodium NaCO will huh. So it will precipitate out hydrated Al2O3, and your silicate, that is sodium silicate, it will remain in the solution. Then, if you heat this aqueous or hydrated Al2O3, you will get pure aluminum. And then uh, different extractive method, like one is molten bath aluminum extraction, and this technique is there. So then the aluminum is extracted from this ore. So this technique is called selective leaching. So here chemical reactivity is plays an important role. Like chemical reactivity of aluminum and silica or Al2O3 or silicate will be SiO2 will be different. So using this principle, so here the Al2O3 is getting separated from SiO2 and other gang particle. Understood? Hello?
Yes, sir. Yes, sir.
Any doubt till now?
All clear, sir.
Okay. And the next one is the particle size difference. So which process utilize this is it based on this principle? Which process do you remember? Particle size difference.
Sir, the fluidized bed.
That is gravity separation that I already showed, right? The flow of water is there, and then depending on the
Jigging?
density and yes,
Jigging?
yes, sieve analysis or jigging. So there is a different size of mesh is there. So larger mesh are at the top and the finer mesh are at the bottom. So if you put your ore on the top and then you shake the whole assembly for some times, you will get the distribution of your particle at different meshes depending on their size. And also you can take the weight of the different particle of the different meshes. Then you can give the size distribution also, like in the weight versus size. So size distribution also, you will find out in your ore or in your minerals. So in this particle size difference, so basically sieve analysis follows this principle. Okay, so I think everyone is clear with all the options, and also it is also clear, right? The for this question the correct answer will be option A.
Yes, sir.
Okay. Okay, so now let's move into the next question. This is the question. The screen is visible. The next question is visible or not? Okay.
It's visible, sir.
Now it is visible, right? Okay. So this is the question number 21 of GATE 2012 Metallurgical Engineering. A polymer matrix composite is reinforced with long continuous ceramic fibers aligned in one direction. The young moduli of the matrix and the fibers are EM and EF respectively, and the volume fraction of the fiber is F. Assuming isostress condition, Young's modulus of the composite EC in a direction perpendicular to the length of the fiber is given by the expression. So, anyone know which will be the correct option?
Sir, for isostress condition, I think option A should be correct.
Okay, you are saying option A. Do you know how to derive this one, this relation or this expression?
Yes, sir. Like, suppose if we take the longitudinal loading, the side by side, if we will that longitudinal arrangement of the fibers, and then we are applying a load. So
Okay.
according to the isostress condition, we can derive it.
Okay, let
Like
me
the
first
sigma
draw
will be.
the assembly. Like, let's say
Yes,
this
sir.
is your composite. In the polymer, there is a reinforced fiber is there. Okay, so now there may be the two condition. One is like this, which is longitudinal direction. You are loading in the longitudinal direction, and another situation may be like this, where you are loading in the transverse direction, right? So in the question it is mentioned, assuming isostress condition. So which condition should we consider then? This one or this one? Longitudinal or transverse?
The first.
Transfer.
Yes. Which one?
I think transfer.
Okay, you are saying transverse. And Sanjit,
Sir, longitudinal.
longitudinal. Okay, so both of you can explain why you are thinking in the longitudinal or transverse it will be isostress. So let's say this F is apply. We are applying F force on in both the cases. Now, in the let's say in the first cases, what will be the stress, and in the second case, what will be the stress? Let's say this area is A, and in this case also, this is the area A for composite, but for matrix, the area total area will be different. It will not be equal to AC, right? So let's say for the area of the matrix is AM, and area of the fiber is AF. And in this case, area of the matrix and area of the fiber will be same, right? Because it is in the transverse direction. Now, in both cases, let's say what will be the sigma C here, what will be the sigma M here, and what will be the sigma F here. In these cases also, sigma C, sigma M, and sigma F. Can anyone tell me?
Sir, I think Prasanna is right. The second case is the isostress because the area is same. So
Okay, yeah. So yes, Prasanna is right. So in this case, your area is also same, and the force also will acting will be same for the matrix phase and same for the uh, fiber. because if the force is difference in the matrix, let's say for the timing I am assuming this force f of m is in applying is on the matrix, and f of small f is being applied on the your fiber. Then if the force value that is different, then what will happen? If let's say fm is greater than ff, then what will happen? Your material, that separation will occur at the interface, means where the matrix is there and where your fiber is there, at that interface the separation will occur. So in this situation your force has to be same on both the phases, means both the matrix and on the fiber. So that's why in this case it will be force will be same. So in case of transverse direction I am talking, so fm is equal to ff, which will be equal to f. So force is also same. So in sigma c will be f by a in this case also. For matrix also it is f by a, and for fiber also it is f by a, right? Since this is the isostress condition. And in this case what will be the sigma c value? In the longitudinal, if you are loading in the longitudinal direction, what will be the sigma c value?
F divided by that the total value of AM plus AF.
Okay, you was saying if means the applied load or applied load, right? And total is am plus af.
Yes.
Yeah, or you can write it is as a by ac. Okay, and now what will be the stress on the matrix? Area I have already told you, am. What will be the force value? Will it be same of f or it will be different?
It will be different, sir.
Yeah, so it will be fm by am, and then for fiber it will be f of f by a of f. Okay, so what mentioned in the question, we have to consider the iso stress condition, and then we have to find out what is the relation between the your elastic modulus in the for the composite matrix and for the fiber, right? So now for the time being just ignore this transverse direction thing, longitudinal direction. So we'll now only discuss with the transverse direction. Okay. So now we know what it is, the isostress condition, and sigma c is equal to sigma m is equal to sigma f, right? Now what is elastic modulus? Let's say elastic modulus is E in general. So in mathematically how you can write it? What is elastic modulus?
Sir, it is the ratio of the stress divided by strain.
Yes. So when you are loading any material in the elastic region, so the stress divided by strain is elastic modulus. Okay. So now in the case of composite, you can write it at EC is equal to sigma C by epsilon C, or you can write as sigma. Okay, let us first write the for each cases, and for a matrix you can write that EM is sigma M by epsilon M, and EF is equal to sigma F by epsilon F. Now, when you are deforming this on the in this direction, let's say after some times, so it will it deforms like this one. So length increases a bit. So from the deformation geometry, what you can write? You can write that the total strain is equal to strain on the matrix plus strain on the fiber, right? total deformation is deformation of the matrix and deformation of the fiber or elastic strain. The sum of these two will be the total strain in your composite, right? Now if you write this epsilon c in terms of ec and sigma c, then you will get sigma c divided by ec is equal to sigma m divided by epsilon of, sorry, I made a mistake. Anyone found out what mistake I made here?
Sir, you also need to consider the volume fraction.
Yes, exactly. So in this case, we also have to consider the volume fraction of the matrix and volume fraction of the fiber, right? Because I'm not considering only one fiber and one matrix. So there is a lot of fiber material will be there. So in terms of fraction, we have to consider. So volume fraction of the matrix into deformation in the matrix, that will be the total deformation for the matrix. And volume fraction of the fiber and deformation or strain in the fiber, that will be the total strain in the fiber phase. So now if we add these two, we'll get the total strain for your composite, right? So here it will be Vm into sigma m and Vf into sigma f by this. So now this is iso stress condition. So sigma c is equal to sigma m is equal to sigma f. So now what we can write? So we can write 1 by elastic modulus in composite is equal to volume fraction of the matrix divided by elastic modulus of the matrix plus volume fraction of the fiber divided by the elastic modulus of the fiber. So this will be your expression, but now only the volume fraction of the fiber that is given. So Vf is f. So what will be the Vm? Vm will be 1 minus f. The total fraction is 1, so Vm will be 1 minus m, 1 minus f. So the expression will be 1 by ec is equal to 1 minus f by em plus f by ef, right? Got it? Any doubt?
Clear, sir.
Okay, everyone understood, right? Okay, so now what will be the expression for the longitudinal direction if we load in the longitudinal direction?
Sir, there, like in the previous case, we equated the stress. So in this case, we will equate the strain in both the direction.
Yeah, so in this case strain will be similar, right? Why it will be same?
Sir, because if the composite is elongating, the fibers and the matrix, they cannot debond with each other, like
Exactly.
at least till the critical stress. So
Yes. So in this case, let's say you loaded it. So let's say after loading, so it is deformed like this. So this is a delta L, right? So change in length will be same for your matrix or and for your fiber, because if it is not same, then your fiber will get detached from your the matrix, right? So in this case, your strain has to be same because the initial length was L for both, and also the change in length is also same for both. So this is a iso strain condition. So your strain in the composite is equal to strain in the matrix is equal to strain in the fiber, right? And already we wrote what will be the expression for sigma c, sigma m, and sigma f, right? Sigma c was force by AC will be force on the matrix, or you can write it as FC. Force on the matrix divided by the area of the matrix, that is the total area of your matrix, and force on the fiber divided by the total area of the fiber. Now if you balance the force, so it should be the total force that is applied, that is FC, should be equal to the Fm plus F of F. The force you are applying, which is getting splitted into the two phases, one for the matrix and one for the fiber, but the force has to be balanced, right? So in this case your force, total force FC will be Fm plus F of F, right? Now similarly, if you write this F of F in terms of your sigma and area, so it will be sigma C AC is equal to sigma M AM plus sigma F AF. Now again we'll write this sigma in terms of F's elastic modulus, that is sigma is E by epsilon, right? So in terms of epsilon and E we'll write, because we have to find out the relationship between the elastic modulus. So it will be E of C divided by epsilon C into AC is equal to E of M divided by epsilon M into AM plus E of F by epsilon F into AF. Now this is iso strain condition. So sigma epsilon C is equal to epsilon M is equal to epsilon F. So this will get cancelled out. So now your EC will be EM into AM by AC plus EF into AF by AC. Now next, how can we write this one? This is this expression is not anywhere in the your options, right? So you have to write it in terms of volume fraction of the fiber and volume fraction of the matrix. So what it will be? Anyone?
So that AM by AC will be replaced by that VM.
Yeah. So you understood why it is VM?
Yes, sir, because the strain is same, na, and so
No. This AM by AC, why it is VM, and AF by AC, why it is VF? Why it is F? What is your volume fraction? Volume fraction means volume fraction of matrix means your total volume of the matrix and volume of the composite, right? Now if the area of the matrix is AM and area of your composite is AC, so now volume is area into length, right? So this is L, and again here the volume is area into length, and you saw that length is same for both the matrix, composite and the fiber. So length will get cancelled out. So VM simply will be AM by AC, and similarly VF will be AF by AC. Understood?
Yes, sir.
Okay. Any doubt in both the derivation?
Clear, sir.
Okay. So for this question, what will be the correct answer then? Which option?
option D, sir.
Option D. This is the expression for loading in the transverse direction. 1 by EC is equal to 1 minus F by EM plus F by EF.
C, sir.
Option C. And if it was mentioned for the isostrain condition, then it will be option A. For longitudinal direction, the expression will be the option A for longitudinal, and this is for transverse. Okay, isostrain and isostress. Understood? So in which condition your composite will be much strong? Means in which sorry, yes, in which loading condition your composite will have a higher elastic modulus?
Sir, in isostrain condition.
Isostrain condition. Yeah, means in the longitudinal direction, right? Okay. Okay, then I'm moving to the next question. This is the question number 35 of GATE 2012 Metallurgical Engineering. The question states that the reduction of FeO with CO gas in a co-current flow is given by the following equation: FeO plus CO is equal to Fe plus CO2, and the delta G naught value is given at temperature 1173 Kelvin. So we have to find out the ratio of the PCO divided by PCO2 for this reaction at 1173 Kelvin. The option A is 0, option B is 0.25, option C is 0.44, and option D is 2.3. So how to approach this question?
Sir,
Delta G is equals to minus RT ln K.
Yes. So at equilibrium, your so basically for any reaction, you can write that delta G is delta G naught plus RT ln Q. Now at equilibrium, what will happen? Delta G is 0. So in this case, it will be your Q will be K, which is termed as equilibrium constant. So in this case, it will be RT ln K plus delta G naught is equal to 0, or you can write uh, K is equal to minus exponential of minus delta G naught by RT, right? So K is the equilibrium constant, that is okay. Now delta G naught is also given, T is also given, so you can easily calculate what is the value of the K. So exponential of minus 8120 divided by 8.314 into T, that is 1173 Kelvin, right? And what will be the K in terms of, if you see this reaction, what will be the K in terms of the partial pressure?
PCO2 by PCO.
Yes, partial pressure of CO2 divided by partial pressure of CO. So this is the your K. So now PCO2 by PCO is how much this is coming?
0.4349.
Then what was the question? You have to find out the ratio of PCO by PCO2. So you have to take inverse of this, PCO by PCO2. This will be 1 by this. So how much this is coming now?
2.29.
2.29 or 2.3, right?
Okay, sir. Got it, sir.
Understood? So what will be the correct option? Option D, right? So understood? Okay,
Yes.
so I had these three questions only to solve for today. So if you have any doubt in any of these question that are solved today, or if you want to ask any question regarding any of the theory also, I'll try to answer. Any doubt in what are the questions that are solved today? Nothing.
Sir, once explain activity, sir. Like last question.
Yes.
That PCO2 by PCO.
Yes. So okay. So this is your reaction. FeO plus CO is equal to Fe plus CO2, right? So now if you write delta G in terms of each element, then what will be? Sorry, each element or each compound. So G of FeO will be G naught of FeO plus RT ln activity of FeO, right? This you know, right?
Yes, sir.
Yeah. And then again G of 0 will be G naught of, that is right like this. Hmm. So in case of gas, activity, how you write activity is basically partial pressure of your gas divided by the total pressure, right? This you know, right? Activity is partial pressure divided by the total pressure. In if in a system, let's say we have two gases A and B. Okay, so the activity is given by the partial pressure and divided by the total pressure. So now in any reaction which is happening at equilibrium and or standard state, like at standard state, so it is considered at 1 atmosphere. So that's why total pressure in this case is 1 atm. So if total pressure is 1 atmosphere, then activity of CO, that will be partial pressure of CO. So then you can write it as partial pressure of CO. Similarly, these are for the product and for the reactant also. G of Fe. This is not G naught. This is G of Fe is equal to G naught of Fe plus RT ln activity of Fe, and again for CO2 also G naught CO2 plus RT ln activity of CO2, or activity for gas you can write it as in terms of partial pressure. Okay, so these are the reactant and these are the product. Now if you add these two and then subtract these two from this product minus reactant, right? Then you will get delta, in the left hand side you will get G of Fe plus G of CO2 minus G of FeO plus G of CO is equal to, similarly in this side we will get G naught of Fe plus G naught of CO2 minus G of FeO plus G of CO, G naught of CO, and then plus RT ln. So PCO2 will be at the top, then activity of Fe, and then activity of FeO into P of CO, right? So this one is termed as delta G, This is termed as delta G, and this is as delta G naught plus RT ln. So this is when you are at equilibrium, this is termed as K equilibrium, and when you are at not at equilibrium, then you can write it as Q. Okay. So in case of equilibrium, you have to write it as K equilibrium, and then delta G will be 0. Okay. So now in this expression, your activity of iron, which is forming in the solid form, and it is pure form. So activity of any solid in any reaction is 1. So in this side also, FeO is in, sorry, FeO is also solid form, right? This is not in the form of gas. FeO is also solid. So in this also, as FeO and in this side iron, both are in the solid form. So activity of FeO and activity of Fe will be 1. So now we have RT ln Q or K equilibrium. That means this is the ratio of PCO divided by PCO, sorry, PCO2 divided by PCO, right?
Like we take activity of any solid is one at equilibrium, sir.
Yes, in reaction activity of any compound that is forming in the form of solid. Okay, so that is considered as 1. It is not homogeneous, what it heterogeneous reaction, right?
Yes, sir.
Or if you think in the terms of partial pressure, then also you can see, uh, let's say in your total system at equilibrium, let's say this is a container where the reaction is taking place. So at equilibrium you have FeO and CO, unreacted FeO or unreacted CO, and the product that is from iron and CO2. So this is a container which is at 1 atmosphere pressure, right? So now activity of any phases can be given as the ratio of that partial pressure of that phase and partial pressure, that uh, total partial pressure, total pressure, sorry. So in this container, will FeO and iron, will they give rise to any uh, means, will they give rise to any partial pressure? No, right? So that's why only gaseous phases are considered, because the gaseous phases contribute for the partial pressure. So that's why the activity ratio for gaseous phases or in a heterogeneous reaction, uh, those are the ratio of the partial pressure by P of total pressure of the CO system, and whichever the product that is forming in the solid form, the activity of those product are 1, is considered 1, right? So that's why simply from this equation we will get the ratio of the PCO2 by PCO, and understood, right?
Yes, sir. Clear, sir.
Okay. Any other question?
All clear for now, sir.
Okay then. Okay then we'll meet on the next Sunday again. So today we are closing this session here. Thank you everyone.
Thank you, sir.
active mass transferring the intensity.